Okay, I am starting lecture for AMT 180 for September 1st. For some reason, there was a problem with the other link that I set this up in. So if you guys find this live, here I am. If not, there will be a recording posted. So I'm just going to get started so that at least you guys have something to watch. I'm doing my best to make these slides a little more viewable. I know that some people said that it was hard to view them. So this is as good as it's going to get. That looks a little bit better to me. I'm going to try and log into my account and see if I can view it and see if that is any better. So just bear with me a minute. Yeah, so I'm viewing it on my screen and whoops, there was an echo. Hopefully that is a little more able for you guys to view these slides. It looks better to me. So I'm going to get started. You guys will be able to watch this later. I don't know why the other link did not work, but we will figure that out later. I see that somebody is logged on. So, yeah, let's get started. Today we are meeting in lab, so I will see you guys shortly at about 5:30. Lecture for today, we're going to talk about AMT 180 aircraft instrumentation. This is what we're going to be reviewing: pressure measuring instruments, types of pressure measuring mechanisms, types of pressure, and pressure sensing instruments in the aircraft. So pressure measuring instruments. These instruments can be found in the flight group and engine group of the aircraft. Remember, we have flight, engine, and navigation. So pressure measuring we're using in the flight group of instruments and the engine group. We also can get direct readings or remote sensed readings from these instruments. So you guys will need to look up what the difference is between those. These instruments can sense changes in pressure, hence the name pressure sensing instruments. We have three types of pressure sensing mechanisms that are used in these instruments. We have the board-on tube, a diaphragm or bellows, and solid state sensing devices. So types of pressure measuring mechanisms. These mechanisms are the board-on tube, diaphragm or bellows, and solid state sensing devices. The board-on tube type of mechanism, often made from brass, bronze, or copper. That's because those metals can be easily malleable. The board on tube is considered very simple and reliable. It can also be used to measure temperature. The board on tube type device is a direct reading or remote reading. Here's a little video describing how the board on tube works. This is something that you guys will need to explain to me in your lab projects.
Okay, so it turns out not all laptops are created equal, which is why it's switching time to a Chromebook designed to make life easy. So you're not stuck waiting.
The operating pressure in hydraulic or pneumatic systems is measured with respect to atmospheric pressure by pressure gauge. The most common pressure gauge design was contrived by Eugene Borden. It used a curved tube design as the pressure sensing element. Pressure gauge with Borden tube contains case, socket, Borden tube, plate, mechanism, dial with scale, pointer, window, ring. The pressure gauge housing is most often made of stainless steel or plastic. Borden tube is made of copper, brass or bronze. The pressure difference between the pressure in the system and atmospheric pressure causes the free end of the Borden tube to deflect accordingly. Movement is transferred via the mechanism to the pointer. At this moment, the pressure decreases and the Borden tube returns to its first position. The accuracy class for pressure gauges is expressed as a percentage of the span. For example, class 0.6 is class for pressure gauges with absolute accuracy better than 0.6% of the nominal full scale reading. The readings of these gauges are slightly different. It's normal. These pressure gauges have different accuracy classes.
Okay, so that's a little short description and presentation on what the board on tube looks like and how it interacts with pressure. I actually want to go back to that video at the very beginning. Oh, I turned the sound off.
The operating pressure in hydraulic or pneumatic systems is measured with respect to atmospheric pressure by pressure gauge. The most common pressure gauge design was contrived by Eugene Borden. It used a curved tube design as the pressure sensing.
Okay, so I want to point out these pieces of this instrument to you guys so that you have an idea of where this board on tube is located. Okay, so we have all the pieces of the instrument here. You know, the face, the dial of it. We have the pointer, the outer casing. And here we have the socket that the board on tube sits in. So here is your board on tube right here. And it's often, like I said, made out of brass, bronze, or copper because they are easily movable with pressure. So this tube sits inside of this instrument and it gets air pressure from the whatever pressure it's sensing and moves this tool, and that's how it moves the indicator with the rest of these pieces. It's mechanisms that turn the dial and you get your reading. Okay, so a little explanation on the board on tube. Examples of instruments that use board-on-tube devices. We have engine oil pressure gauge, hydraulic pressure gauge, oxygen tank pressure gauge, and de-ice boot pressure gauge. So all of those gauges are examples of instruments that would use the board-on-tube device for pressure reading. I'm just going to check the chat here and see if there's any questions. Yeah, I see. It looks like, I know, dang, you're the only one here. The link that I attached in Canvas did not work. I couldn't get it to work for some reason, so I had to make a new one. So I know a lot of people are probably really confused during this time, and you guys are just going to need to be patient with us. There's a lot of different factors for this online teaching stuff. So at least I can get this recording out here and you guys can view it at a later time. Okay, so moving on. We're going to talk about a diaphragm device that's used in pressure sensing instruments. So diaphragm is a hollow, thin-walled metal disc. That disc expands when pressure is introduced, and it can be sealed, which then it would be called an aneroid, or filled with gas to atmospheric pressure. Okay, so this is actually a training film by the US Navy, and I kind of like it. I'm gonna see if you guys can hear this film, but we're gonna watch it after my lecture because it's a long film. But it has a really, really good description about how diaphragm instruments work. Okay, so bellows. Bellows are when a number of diaphragm chambers are connected together. It makes an accordion-like shape, and it's useful for measuring the difference in the pressure of two gases. Examples of instruments that use a diaphragm or a bellows type device: the altimeter, vertical speed indicator, cabin differential pressure gauge. This is in pressurized aircraft only, and the manifold pressure gauge. All of these types of instruments use a diaphragm or a bellows device for the pressure reading. And your handbook, the 8083, has some really good pictures of these devices. So here we are in the 8083. In chapter 10, that's the version that's online, which is the most recent. Here we have your board-on-tube. This is a really good picture that describes the board-on-tube. This is that copper, bronze, or brass piece of hollow metal. So that's a really good, has a good description in this book of how that operates. And here's a picture of your diaphragm, pressure diaphragm. So this thin-walled piece of metal, we have pressure that's introduced to that thin wall. And when that senses a difference in pressure, it moves this needle, which in turn moves the gear and in turn moves the dial. So you guys will need to know all of those devices and be able to explain them for an oral checkout in your labs. Okay, and again, the gauges in the aircraft that use those diaphragm and bellow devices. Solid state sensing devices. So these have a digital output. These are like the newest and greatest, devices. Everything's kind of going electrical. in reading instruments and really everything. Everything that can go electrical will go electrical as far as aircraft. Okay, so it has a digital output, exhibits varying electrical output or resistances with changes in pressure. That's how the solid state sensing devices operate. This mechanism is a remote sensing system. So this solid state sensing devices do not have a direct sensing system. They have a remote sensing system. So the remote sensing system, meaning remember we talked about this last time, we have the direct sensing, which is like one instrument and all of the devices are encased in that instrument. It is able to sense and display what that reading is within one instrument casing. A remote sensing system is when you have a piece of equipment that can sense in this instance, a pressure change, and then it converts that sensing into an electrical signal and sends that to the display at a different location in the plane, usually in the cockpit, the display in the cockpit. So this is a short video on piezoelectric devices, which is what makes sensing devices work. Let me see if I can pull it up here. It didn't paste in a link.
Hi, I'm Clint, and welcome to AMT. There are many uses for piezoelectrical devices in today's vehicles. We use to see their effects without a second thought. But can you diagnose a fault in one of these, not knowing how they work? Let's take a closer look at piezoelectricity. A knock sensor is a piezoelectric vibration sensor. When engine detonation occurs, the vibrations are transmitted through the engine block to the sensor body. Inside the sensor is a ceramic sensing disc. The vibrations from the detonation create pressure on the ceramic that is proportional to the knock. The ceramic generates a voltage based on this pressure and is signalled to the ECM for conversion and interpretation. With a scope attached to the sensor, any substantial vibrations will be detected and reflected as an alternating current signal. These sensors are signal generators, and as such, they don't require a reference voltage to operate. The main reason for using piezo technology is because of its accuracy and reliability. In this air conditioning pressure sensor, we were able to read very small changes in refrigerant pressure by amplifying the signal. This is a sample of the hundreds of training videos we have available, covering everything from technical fundamentals, diagnostic procedures, equipment and wiring diagrams. Automate is simply the best training available. So why not join us today? Start training and be the best technician you can be.
Okay, so a little description about piezoelectric operation. Examples of instruments that use solid state sensors. Nearly any and all pressure sensing instruments can be used with solid state sensor devices. That's the way that aircraft are going now. You know, they're going to all glass cockpits, and everything is really being converted to an electrical signal that you can view on a screen. So the big difference between solid state sensors and diaphragm or bellows or board on tubes is that you can do either direct sensing or remote sensing depending on the device, and solid state sensors, you just automatically are doing remote sensing only. Types of pressure. So we're going to go over these 4 different types of pressure. We have absolute pressure, gauge pressure, differential pressure, standard pressure. What is pressure? Pressure is the comparison between 2 forces. Okay. Absolute pressure. Absolute pressure exists when a force is compared to a total vacuum or absolutely no pressure. Absolute pressure, many instruments use absolute pressure values with an aneroid, which remember what an aneroid is, we just went over that in the diaphragm section. Examples of instruments that use absolute pressure, we have your altimeter, rate of climb indicator, and manifold pressure gauge. Gauge pressure. So gauge pressure is the difference between the pressure to be measured and atmospheric pressure. Gauge pressure is the most common type of pressure measurement. When you fill your car tire, your reading is a gauge pressure reading. So if you fill your car tire to 33 PSI, you're going to read it with a gauge either on the air hose or a separate gauge. And that gauge is going to give you a gauge reading. It doesn't give you an absolute reading, it gives you a gauge reading. That's what that gauge is reading. Gauge pressure eliminates the need to measure changing atmospheric pressure constantly. Gauge pressure should be assumed unless otherwise indicated or unless the pressure measurement is of a type known to require absolute pressure. An example of that is your altimeter. Your altimeter is known to require absolute pressure. Okay, so gauge reading is an assumption that we make that can be used, in general practice. Because we are reading a lot of gauges, we're using a lot of gauges to read measurements. So unless it's something that is kind of a set standard that we know uses some other type of pressure reading, or unless it is directly pointed out to you that you need to use absolute pressure or some other type of pressure reading, then the assumed pressure reading is going to be a gauge pressure. We also have differential pressure. Differential pressure, do we skip one here? Okay, so differential pressure is used to compare the pressure of 2 different elements. This type of pressure is used in an instrument reading, would be called a differential pressure gauge. So if we are trying to find a reading for differential pressure, we're going to use a differential pressure gauge. Some examples of where differential pressure is read would be your turbine EPR gauge or your airspeed indicator. Okay, standard pressure. Standard pressure is an established or standard value that has been created for atmospheric pressure. So I think that many of us have probably heard of 29.92 inches of mercury. Hg means mercury. That's a standard pressure value. 14 psi is a standard pressure value. They have made those standard values to account for atmospheric pressure. Okay, we have our pressure sensing instruments. So our pressure sensing instruments are going to be our engine oil pressure, manifold pressure, EPR, engine pressure ratio, our fuel pressure, hydraulic pressure, vacuum pressure, and pressure switches. This is a list of all of the pressure reading instruments that we could possibly have in an aircraft. So in this class, in these labs, you guys will be looking into the information on these instruments, and you will need to tell me which instruments are a board-on-tube device reading, which instruments use assumed gauge pressure, which instruments use absolute pressure, how those instruments work, how does the fuel pressure instrument read that pressure, what does the mechanism inside that instrument do, you know, to give you that reading. I'm going to go back and I want to play this video because it has a really good description of diaphragm devices used in instruments. Okay, hopefully you guys can hear it. I'll try to turn it up, but it's a little like fuzzy. Okay, so I'm going to read this because I know it's probably difficult to read. It says forward. So this is a film made by the U.S. Navy training. Instruments vary in many ways. The mechanism, design, and dial calibrations for any given instrument may be slightly different depending on who manufactures. So calibrations for any given instrument may be slightly different depending on who manufactures it and the type plane in which it is used. However, the instruments depicted in this film have the same basic function and operate on the same fundamental principle as all other instruments of their type. The graduations on some altimeters, for example, represent 10 feet for each mark on, and on others, mark means 20 feet. Some airspeed indicators register higher speeds than others. Okay, so on the dial of some rate of climb indicators, an arrow points to up and others point to down, while other similar indicators omit these arrows completely. It is presumed that you who are watching this film are interested in the function and operation of these instruments. So it is presumed that in this film, you are interested in the function and operation of these instruments rather than in the slight variations in appearances and design.
On the instrument panel of a modern aircraft, there are three diaphragm instruments known as flight instruments. They are the airspeed indicators, the rate of climb or vertical speed indicators, and the altimeter. They are all pressure-activated instruments that depend on a physiostatic system for the air pressure to operate them. All three receive static or still atmospheric air pressure. And the airspeed indicator also receives pico or impact air pressure. The shape and location of picostatic tubes vary with the type plane, but they all work on the same principle. This is called the shotgun type. As the plane moves forward, impact air enters port A and passes through tubing to the diaphragm of the airspeed indicator. A baffle and a moisture trap stop most of the moisture from entering the tube. The formulated water moves the system through drain holes. This is the pico or pressure side of the system. Static or still air under the prevailing atmospheric pressure for the altitude at which the plane is flying enters the static tube. The static hole admits only the existing atmospheric pressure through static lines to the three diaphragm instruments. The pico and static tubes are sealed from each other. When the aircraft is in flight, the air pressure in the pico side is always greater than in the static side. Moisture in the static tube escapes through the static air hole. Electric heating elements prevent icing and keep the drain holes open in both the pico and static sides. The airspeed indicator tells how fast the plane is flying in respect to the air around it. From this reading, the pilot knows if he is flying within the safe minimum or maximum airspeed of his particular aircraft. Also, an increasing speed during instrument flying with a constant power setting tells the pilot his plane is descending. A decreasing speed tells him he is flying. The airspeed indicator operates by different air pressures acting upon a diaphragm. Movement of the diaphragm is transmitted by impulse to a pointer of the dial on the instrument panel. The air pressures are obtained from the pico-static tube. The airtight case containing the diaphragm impulse receives air from the static line. Thus, the air inside the case is always under the atmospheric pressure of the altitude at which the plane is flying. The pico line is directly connected to the diaphragm. Impact air entering the pico tube causes the diaphragm to expand as the speed of the plane increases, and contract as the speed decreases. This expansion and contraction is actually very slight, and must not only be transmitted, but amplified by the linkage system to give a reading on the dial. Let's see how this works step by step. When the diaphragm expands, the locking shaft is stirred. This motion is transmitted to the section, which in turn rotates the pinion on the tapered shaft with its connected point to give a reading on the dial. The hairspring, being tightened as the speed increases, introduces some each top and causes it to follow a contracting diaphragm movement when the speed decreases. The airspeed indicator is calibrated to give true airspeed only at sea level and under standard atmospheric conditions, which are barometer 29.92 inches of mercury or 1013.2 millibars, and temperature 59 degrees Fahrenheit or 15 degrees centigrade. altitude or temperature, the instrument gives only the indicated airspeed. The airspeed selection scale on any flight computer must be used to obtain true airspeed. However, a rule of thumb is that selection for altitude error may be made by adding 2% to the indicated airspeed for every 1,000 feet above sea level. For example, if at sea level, your indicated airspeed given on the instrument dial is 150 knots, that is also your true airspeed. However, at 2,000 feet in less dense atmosphere, if your indicated airspeed is 150 knots, then your true airspeed is 150 times 2%, or 3 knots more for each 1,000 feet of altitude. So at this 2,000 foot level, 6 knots must be added to the indicated reading to obtain a true airspeed of 156 knots. At 4,000 feet, an indicated airspeed of 150 knots means a true airspeed of 162. At 6,000 feet, the true airspeed is 168. And at 8,000 feet, an indicated airspeed of 150 means a true airspeed of roughly 174 knots. The rate of climb, or vertical speed indicator, is essentially a differential pressure gauge. It shows the rate of ascent or descent of a plane in feet per minute. If the indicator is at the 0.5 mark clockwise from zero, it means you are climbing at the rate of 500 feet per minute. If it is at the 1 mark, you are climbing at 1,000 feet per minute. As you stop your climb and return to level flight, the pointer will return to zero. In descending, the pointer follows a counterclockwise course and gives the rate of descent. The rate of climb indicator is composed essentially of an airtight piece containing a diaphragm, which is centered directly to the atmosphere through a connector tube to the static source of the pitot-static system. A diffuser valve assembly is also connected to the static source. This assembly, which allows air to enter or leave the case at a restricted rate, consists of a small porcelain capillary tube and a bimetallic temperature compensator. There is a linkage system composed of a link, an arm, a rocking shaft, a sector, a pinion, and a pointer. Let us suppose the aircraft is descending. Air enters from the static source of the pitot-static system. It goes directly to the diffuser valve assembly and to the diaphragm. The diffuser permits the air to circulate forward at a predetermined rate. Since we're descending into denser air pressure, the air is slowly entering the case. However, this denser air pressure acts directly and immediately on the diaphragm. Since this pressure is greater than the gradually increasing pressure in space, the diaphragm expands. Now suppose we stop descending and resume level flight. Within seconds, the air feeding into the diffuser completely fills the case. The air pressure inside the case now equalizes that acting on the diaphragm. And the diaphragm returns to its original position. Now let us suppose we start flying. The air pressure inside the diaphragm and static tube immediately become less as the plane moves up into less dense air. Pressure inside the case also begins to lessen as air gradually seeps out through the diffuser assembly. However, the pressure inside the case is now greater than that inside the diaphragm, and the diaphragm begins to collapse. When the plane resumes level flight at its new increased altitude, the air pressure inside the case still equalizes that inside the diaphragm, and the diaphragm returns to its normal position. Basically, here's how the making works when a plane is descending. As the diaphragm expands, it gives the leg a pushing movement. This moves an arm, which turns the locking shaft. The locking shaft turns the attached section, which is meshed with the pinion. As the pinion turns, the connected wire gives a new reading on the die. The airspring simply keeps the linkage taut and prevents backlash. Let us suppose this is the position of the diaphragm at linking with the plane in level flight. As the plane descends and the air becomes denser, the diaphragm expands and the linkage operates because a new reading on the die. Returning to level flight, the pressure inside the seat rapidly equalizes the pressure inside the diaphragm, causing the diaphragm to contract to its original position, and the plunge to return to zero. The same action, in reverse, occurs during the clock. The altimeter is essentially an analog barometer that translates inches of mercury into feet of altitude. The free hand indicates hundreds, thousands, and tens of thousands of feet. Thus, this reading would indicate 400 feet. This would be 1,400 feet, and then 20,000 feet. Air from the static source of the physiostatic system enters the aircraft instrument case. Increasing atmospheric pressure as the aircraft ascends acts on the multiple diaphragms, causing it to expand. Increasing pressure, encountered as the plane descends, causes the diaphragm to contract. This diaphragm movement is transmitted by multiple gears to the two hands on the dial, which show hundreds, thousands, and tens of thousands of feet. In its simplified form, this is the operation of the linkage. As the diaphragm expands, it pushes a link which in turn rotates the locking shaft. This movement is imparted to the sector, which greatly amplifies the linear motion of the diaphragm. The mesh indicator turns the tapered hand shaft, and the connected pointer in a clockwise direction, indicating an increase in altitude. The airspring keeps the mechanism taut. In descending, the action is reversed. In climbing or descending, a 1/4 inch movement in the diaphragm sends the large plane 35 times around the die. The diaphragm is sealed with a constant internal pressure of 29.93 inches of mercury, or standard sea level pressure. This gives an indicated reading of 0 on the die. As the aircraft ascends, the decreased atmospheric pressure allows the diaphragm to expand, and a higher reading is shown on the die. The action is reversed in descent. In the same manner, a change in atmospheric pressure will cause a different reading on the die. When you are flying at 1,000 feet above sea level under standard atmospheric conditions, barring installations and/or mechanical errors, your altimeter dial will show an altitude of 1,000 feet. Now, suppose you entered a low-pressure area where the barometric reading, radio to you from the ground, was 29.71 inches of mercury. Your altimeter would read approximately 1,200 feet, an error of 200 feet, since your actual altitude would still be 1,000 feet. The same would be true in reverse if you entered a high-pressure area. To correct this error, you turn the adjustment knob until your barometric setting corresponds to that radio reading from the ground, 29.71. The synchronized gear mechanism automatically changes the altimeter pointers back to the indicated altitude of 1,000 feet. During flight, there can be frequent radio contact to determine barometric pressure and the necessary corrections made. Always remember that the indicated altitude given by your altimeter, when corrected for temperature, is the altitude above sea level. If you are flying at a corrected altitude of 7,000 feet just above some clouds, your absolute altitude above a 6,800 foot mountain is just 200 feet. Remember that your three diaphragm or pressure-activated performance instruments all receive their activating force from the pitot-static system. The airspeed indicator utilizes the difference in air pressures received from the pitot and the static tube. It is the only one to receive both static and pitot or impact air pressure. The rate of climb indicator is activated by the rate of change in static air pressure. And the altimeter is operated by changes in static or atmospheric pressure, acting on a sealed diaphragm, containing a trapped pressure of 29.92 inches of mercury, the standard sea level air pressure.
Okay, so that's it for lecture for today. I will see you guys in lab in about 30 minutes from right now. And we will discuss some of these technical issues and stuff like that. I know I had a problem with the link today, so you guys will have time to watch lecture in lab today. That's it. I will see you guys in lab.